Hi everyone, I'm Pranjay Shyam and I'll be presenting a brief overview of our paper, Perception-Aided Image Restoration for Natural Driving Conditions. So before moving forward, I would like to elaborate upon the problem description and the definition. Current image restoration algorithms are degradation specific in nature, therefore these cannot be deployed in an automotive setting, where a natural condition can comprise of multiple degradations to exist simultaneously. This necessitates integrating a degradation identification mechanism before the application of the corresponding restoration algorithm. Recently, end-to-end solutions for performing image restoration are also proposed, but they're either confined to static natural scenes or require the generation of synthetic weather augmentations to produce noisy images from the clean one as the training dataset. This results in a limitation wherein the former fails to capture diverse scene interaction, whereas the latter introduces a performance gap due to the inaccuracies in the degradation modeling, as these degradations are considered one at a time. Furthermore, these restoration algorithms, apart from being computationally complex, have demonstrated reduced performance when applied on images captured from different sources having distinct camera response functions compared to the training dataset. And finally, we highlight that current evaluation mechanisms for image restoration focus on perceptual aesthetics of restored images as desired from a human visual perception viewpoint. However, such restored images adversely affect the performance of downstream perception tasks such as feature matching, object detection, semantic segmentation, depth estimation, and simultaneously localization and mapping. This is due to the fact that image restoration algorithms do not have any guidance on where the objects of interest for the accurate performance of these algorithms lie. Hence, to overcome these limitations, we propose the following four contributions in this work. First, to ensure local degradation diversity within training samples, we generate a combination of instance-aware local and global degradations. Second, to restore a degraded image in a compute-efficient manner, we propose a two-stage local-global image restoration framework that disentangles image restoration into local image enhancement and global image restoration. Third, to ensure improved perceptual quality results in improved lens prediction, we utilize lens prediction tasks such as segmentation and depth estimation during the optimization process. Finally, to ensure robustness towards distribution variations arising from camera ISP, we propose the utilization of multiple learnable inverse ISP pipelines to simulate the camera response functions of unique cameras for the training samples. Focusing on non-homogeneous and non-linear degradation generation, we highlight that in the absence of real datasets capturing diverse driving conditions, there is a critical need for a mechanism to generate non-homogeneous and non-linear degradations. By incorporating such degradation variations, we expand the degradation space, leading to a more holistic training approach, improving the performance of image restoration algorithms. We observe such an approach to result in restoration algorithms being more robust and capable of handling complex real-world degradations without requiring real paired datasets. Construct the proposed mechanism by combining instance-guided degradation generation, illumination change, and flare modeling augmentations. Now, given a clear image and an instance map as the inputs, we generate instance-guided degradation by considering global degradation space to be composed of rain, snow, and fog, whereas the local degradation space is defined by motion blur, water droplets, and noise augmentations, which are generated using the AMOG library. Since the global degradation can be non-homogeneous in nature, we randomly apply different degradations to different instances present in an image. Furthermore, we apply region augmentation techniques to randomly degrade regions within an image. Different from prior synthetic augmentation approaches, our approach can model realistic weather variations by accounting for scene dynamics using localized degradations. Now, in order to introduce non-linearity of the degradation, we use degradation order that specifies the number of iterations that particular degradation type would be applied on the instance. As this is a data preprocessing step, we limit the order of non-linearity to 3 to ensure a compute bound. By allowing nonlinear and non-homogeneous degradations, our algorithm significantly expands the degradation space, enabling a more holistic training of the image restoration algorithms. For synthesizing low-light images, our approach draws inspiration from the methodology wherein to emulate the characteristics of low-light condition, a combination of both linear and gamma transformation are utilized. These parameters, alpha, beta, and gamma, are randomly sampled from a uniform distribution to introduce diversity and naturalness into the generated images. While this pipeline models the illumination changes, it does not account for noise distribution, which we include to obtain a faithful representation of low-light images by integrating a term eta that represents image noise arising from photon shot noise, red noise, and the quantization noise. The photon shot noise is modeled using a Poisson distribution accounting for the randomness of the photon detection, whereas red noise, which accounts for long-tail distributions, is modeled with the Tukey lambda distribution. Quantization noise resulting from limited discrete levels in the digital space is modeled using a zero-mean Gaussian distribution. By incorporating these noise models into the degradation generation pipeline, we accurately capture noise sources within the image signal processing of the camera. Now we provide a brief overview of the perception-aided image restoration pipeline, which is composed of two stages. Stage 1 focuses on local image restoration based on the motivation that while task-specific neural networks have shown promise in image restoration, their computational requirements make them impractical for real-time applications for scenarios where multiple degradations exist simultaneously. Moreover, these networks often perform global image restoration even for regions that do not require any restoration or enhancement, as the normal natural degradations are non-homogeneous in nature. So to overcome these limitations, we propose a novel approach for local image restoration and enhancement using traditional image processing operations such as gamma correction, white balance adjustment, noise removal, sharpening, tone mapping, fog removal, and pixel corruption correction. With an emphasis on localized operation, our method efficiently and effectively restores and enhances specific regions of interest, improving the image quality while avoiding unnecessary computational overhead. Now, to achieve this, we utilize a pre-trained convolutional neural network trained on ImageNet and adapt the architecture by removing the final pooling layer and adjusting the output dimension, defining the factor and weight for each image processing operation using a 1x1 convolution. Here, factor refers to the intensity of the operation, and weight refers to the contribution of an operation towards final restoration. This modification allows us to perform patchwise restoration determined by the receptive field of the last convolutional layer. By removing the pooling layer, we preserve the semantic information within each patch, enabling localized restoration capability for target enhancement and restoration of specific image regions. The patchwise representation offers a comprehensive understanding of local image features, facilitating precise restoration operation. Now, given a degraded image, we first generate feature embeddings using a convolutional neural network, which are then filtered for specific image processing operations. A holistic overview of the proposed algorithm mechanism is shown in this figure. This stage focuses on global image restoration. While localized operations can restore localized degradations, there are certain limitations such as boundary artifact in the final restored image and inadequate restoration when the degradations cover an area beyond the patch size, which is determined by the receptive field size of the underlying CNN, leading to inaccurate restoration results. To overcome this, we introduce a lightweight unit architecture in the second stage of our approach, which is designed to recover and restore the partially restored image obtained from the first stage. Moreover, we leverage the pixel corruption score generated in the first stage as an attention guidance mechanism, highlighting the areas needed more restoration. We reduce the computational complexity of the unit architecture using split convolutional block and selective kernel fusion, for which we would redirect the listeners to the paper for more details. Now, since the proposed two-stage restoration mechanism effectively recovers degraded image, producing visually pleasing results, however, there might be some adversarial patterns that can degrade the performance of the perception algorithms. To mitigate this issue, we delve into the analysis of the error-causing area, specifically focusing on the image signal processing pipeline, which can influence the performance of the restoration algorithms as the images captured from the different camera sensors tend to alter the performance due to the bias of restoration networks to a particular camera response function. Since this adversarial restoration affects the underlying perception task, we integrate such algorithms during the optimization process of the restoration network to ensure consistent performance. Furthermore, we introduce multiple camera response functions to expand the color space so that the underlying restoration network can restore images without any adversarial pattern. So deviating from using coarse perception tasks during the optimization, we leverage dense perception tasks since commonly used object detection algorithms, which are used for the optimization process, are robust towards localized degradations, and therefore such restoration algorithms cannot recover minute imperfections. On the contrary, dense perception tasks such as segmentation and depth estimation are sensitive towards minute localized imperfections which may not be visible to the human eye. Hence, utilization of such algorithms during optimization can provide benefits against generating adversarial patterns during the restoration phase. To integrate semantic and depth information, we leverage SegFormer and the Zoe depth networks for performing semantic and depth estimation. We now provide some qualitative results of the proposed approach and compare it to general purpose image restoration algorithms such as AirNet, GIQE, WD, and a reference image which was captured in clear weather conditions. We also provide some quantitative results captured for both the task-specific image restoration networks as well as general-purpose image restoration networks for automotive datasets such as AC/DC and DENS. I would like to now end my presentation and thank you for your attention.